Hello, everybody, and welcome back. Today, we are going to be continuing with our financial applications for Unit 4 of Grade 11 functions. Today we're going to specifically be talking about calculating the number of payments. So, just a reminder, our equation for how to calculate compound interest in general is A, the accumulated amount, is equal to P, the principal, times 1 plus R being the interest rate, to the power of n, which is the number of compounding periods, right? So the number of times that we actually do the compounding. It doesn't necessarily matter how much time has passed per se, it's about how many times within that time did we actually compound. That's what we want to know. How many times did this compounding effect of the interest rate actually apply? Now, in this case, we're going to specifically be calculating and the number of payments. In the previous video, we talked about calculating things like A, the interest itself, and also P, but we never really talked about how to calculate N in that video because the thing is, we're going to need to use logarithms in order to do this, so it's going to be harder than what we're used to. So here we're going to just quickly review logarithms, right? So basically we can use logarithms whenever we have the power that is the unknown, right? Now, previously, before learning logarithms, how would we have solved this? We might have said, okay, well, let's use trial and error. Let's try 4 to the power of 5 and see if that works. And if that's too low, then we'll try 4 to the power of 6. And if it's too high, we'll go back down to 4 to the power of 4. And, we'll kind of try and figure it out an approximate answer that way. But there is a better way to do this. Now that we're at grade 11, we are going to use the better way, which is logarithms, right? If you're below grade 11, it's probably acceptable just to use the trial and error method. If you're grade 11 or above, then we would like to try and learn the logarithm method. But of course, you can learn the logarithm method earlier than grade 11 if you wish to do so. Okay, so now let's talk about how we would use logarithm method on this one. Just in general, logarithm, or actually, you know what? X to the power of A equals to y. This is the same as logarithm with the base x, y is equal to a. So notice here, we're isolating a. The logarithm allows us to isolate a, which is good. Whenever we don't have a base, right, if we don't have a specific base, that just means the base is automatically 10. That is just the normal. Okay, so in this case, how are we going to use this definition in order to figure out x to the power, or 4 to the power of what, equals 1,325? Well, let's see, logarithm with the base 4, 1,325 is equal to x is the way we do that. Also recall that log xy like this is equal to log y over log x. So we can actually just type this into our calculator. If you have a scientific calculator, I want you to type in log 1,325. Okay, which is going to be about 3.122 over log 4, which is 0.602, equals to x. So therefore, x is equal to, well, let's see what that is, 3.122 divided by 0.602 is equal to 5.186. So basically, to check this now, what I'm going to do is I'm going to put in my calculator 4 to the power of 5.186. And just a reminder, it's not going to actually get us 1,325 exactly because 5.186 is an approximation, right? We had a much longer decimal than that, but it should get us extremely, extremely close, like within a few points of 1,325. And if it doesn't, if it gets us something totally different, then we've done it wrong. So let's check that. Let's put in to our calculator 4 to the power of 5.186 equals, okay, so I got 1,325.2, so less than one whole unit. away from 1,325. So our answer was slightly bigger, right? Just because of rounding, but that's no problem. That's still okay. We're never going to be able to put the exact answer unless they were okay with us just stopping here and saying, well, this is the answer, right? This is our exact answer. This is our decimal approximated answer, and they want a decimal approximated answer. They don't want us to say, oh, how many payments do you have to pay? You have to pay log with a base 4, 1,325, right? They don't want you to say that, right? So they're most likely in this case looking for the decimal approximated answer as opposed to the exact answer. Good, very good. All right, so now I'm going to do the same thing over here. I'm going to say that this one, we have log with the base 11.25, 1,000 is equal to x. So that means x is equal to log 1,000 over log 11.25. Now, luckily, I already know what log 1,000 is, right? Because again, this log has a base 10 automatically, even though it doesn't show there. And we know 10 to the power of 3 is 1,000. So log 1,000 is easy. I don't even need a calculator for it. It's just 3. So what is log 11.25? Let's see. That I don't know. I will admit I don't know that one. Okay, that one's going to be 1.0511 approximately. Oh no, I guess let's just end it there. Just 1.051. And then let's divide that. So 3 divided by 1.051 is equal to 2.8544 approximately. So again, if I put into my calculator 11.25 to the power of 2.8544, I should get something very, very close to 1,000, right? Within a couple of points of 1,000. And I do, I get 1,000.94, which I guess is closer to 1,001, but still that is close enough that we have done the problem properly. And again, this is just a decimal approximation that should get us very, very close. This is our exact answer, right? Okay, very good. All right, so now we're going to use these logarithms that we just reviewed in order to solve more difficult problems regarding the calculating the number of payments specifically. So example 1 says, how many years will it take to grow $400 to $1,000 if it's invested at a rate of 15% compounded annually? So first thing I'm going to do before I even, start this question is I'm going to write down the equation that I know we will need for compound interest. The equation is that the amount accumulated is equal to the principal times 1 plus the interest rate to the power of n. And I'm going to also write down what is given. So what is given to us in this equation? They're asking how many years it will take. So they want to know what's the number of payments, right? Because it says compounded annually. So the number of payments is actually the same as the number of years in this specific case because it's compounded once per year, right? That's what we mean by compounded annually. How many years will it take $400 to grow to $1,000? Well, that means $400 is our original principal that we're putting in, and the amount that's accumulated is $1,000, right? We need to know how many years is it going to take for us to get from $400 to $1,000. And my guess, probably a lot of years, right? It's more than doubling to get from 400 to 1,000, but the interest rate is also 15%, so actually maybe not that many years because 15% is a pretty unrealistically high interest rate. If you're getting that interest rate, you got pretty lucky. So R is going to be 0.15. And now we have enough information to solve for N. So let's do that. $1,000 is equal to $400. 1 plus the interest rate, which is 1.15 to the power of N. Then we're going to have 5 over 2 equals 1.15 to the power of N. And at this point, that actually I'm going to switch 5 over 2 to 2.5 just because I would like everything in decimals in this case as opposed to having some fractions and some decimals, but it is going to be the same thing, right? 1,000 over 400 is going to be 2.5 or 5 over 2, same thing. And now I'm going to apply my logarithm. So I'm going to say, well, here we have a log with a base 1.15. and our answer is 2.5, and the power we're looking for is n. And again, this is equal to log of 2.5 over log 1.15. Now, log of 2.5 is 0.3979 approximately, or you know what, we'll put 4 as well. And then log 1.15 is equal to 0.06069, which would be 70, like that. And that is equal to what? Let's see, 0.39794 divided by 0.06070 is equal to 6.556, I guess. Okay, and again, this is a decimal approximation, but if I take 1.15 to the power of 6.556, I should get about 2.5, and I get 2.49997, right? So, and then some other stuff. So, again, about what we're looking for. This is our approximation. So, therefore, it will take about just over 6.5 years in order for us to grow $400 to $1,000. So it'll take quite a few years, even with this very good interest rate that we're getting. So that's going to be our answer. Is it will take about 6.556 years to grow that money. All right, very good. Let's move on to example 2. Example 2 says, if $1,000 was borrowed at a rate of 14% compounded annually, how long would it take for the balance to become $23,000? Okay, so again, you know, $23,000 from when $1,000 is all we borrowed, that's going to take a very, very long time, even though 14% is a very high interest rate. So I'm expecting it to be a lot of years, and in practice, you'd actually probably be taken to collections if you really weren't paying for so long that your balance became $23,000. So I'm expecting this one to be a lot of years, maybe like, you know, 30 plus years. Let's see if I'm right. I'm not sure, but it's definitely going to be a lot of years. That is for certain. That I do know. So again, let's write out our given. So we know that the amount accumulated, the accumulated balance would be 23,000. Our original balance, our balance that we actually owe in terms of what we actually spent that we owe somebody, is $1,000. And the R for the interest rate is 14%, which is 0.14. And N is the number of compounding periods, which in this case is going to also be the number of years because it's compounded annually again. And so that's what we need to figure out. So let's do that. 23,000 equals to 1,000. 1 plus r, so 1.14 to the power of n. Now 23,000 over 1,000 is 23, so 23 equals 1.14 to the power of n. And that means n is equal to the logarithm with the base 1.14, 23. So that's equal to logarithm 23 over logarithm 1.14. And let's see, what's that equal to? We're going to need a calculator at this point to solve that. Okay, so 1.3617 over 0.0569 is equal to 23.93 approximately. Okay, which that makes sense. Let's see actually. 1.14 to the power of 23.93 is almost exactly 23. Awesome. All right, well, very good. All right, there we go. So that's going to be the answer. Therefore, it'll take 23.93 years. So if we want to round to the nearest year, it'll take 24 years for our $1,000 balance to finally become $23,000. So, it's going to take a very long time to get there because that's quite a large balance, especially considering that we only started by borrowing $1,000. Very good. Very, very good. All right.